Hello everyone, this is a video covering Chapter 12 problems, specifically homework 9. I'm going to go through the 6 problems that I assigned. I'm going to do that in a new way. For those of you who just want a hint or a little bit of help, I'm going to give you kind of an overview of the problem and a hint that might help you finish the problem without too much explanation. And then I'll go through and I'll go through every little bit and solve it piece by piece. So if you just want a little bit of help, you can watch the first part of this video. And if you actually want to see how we do it step by step, that will happen at the end. So before I get started on the problems themselves, I want to talk about the equations that we need to know and the concepts we need to know. So chapter 12 focused on equilibrium, and equilibrium only means, well, static equilibrium, I should say. Static equilibrium means that the whole system is not moving and it's not rotating. And therefore, the sum of the forces in the x direction have to equal 0, and the sum of the forces in the y direction have to equal 0. That's easy enough to understand. If we add up all the forces, they better equal 0, because otherwise the system's moving and it's not in equilibrium. And the third condition is that the sum of all the torques also has to be 0, so that the system isn't rotating. So basically how we solve these problems is we find all the forces in the x, set them equal to 0, find all the forces in the y, set them equal to 0, find all the torques, set that equal to 0, and we can use that to solve for our variables. There's one additional concept that you need to know, and that is that this is about any axis in the system, okay? And that helps us because any torques that are being applied any forces being applied at the axis of rotation result in 0 torque. So we can use that to eliminate forces we may not know, we may not want to know, or just to make our problems easier to solve to get the information we want. So basically what we do is we pick axis of rotation, we find all the torques about it, we find all the forces, and we set them all equal to 0. And from there we solve our problem. When it comes to elasticity, we're actually only going to talk about tension forces. Elasticity in the chapter talks about tension forces and then deflections when like a rod is bent, and it talks about hydraulic stress when pressure causes a volume change. We're just going to talk about elasticity, which is, say, a wire is subject to some perpendicular force which causes it to lengthen or contract. So a wire of length L is subject to some change in length due to some force perpendicular to the cross-sectional area. And if we assume a wire is circular, then this would be pi r squared, r of the wire, the radius of the wire. This equation actually gives us pressure, which is force over area, and this is the cross-sectional area mentioned above, is equal to something called Young's modulus times the change in length over the initial length. Those problems are really going to be just plug and chug. I gave you one on here that has a little bit of a wrinkle. I'll talk about what that is. It has really nothing to do with the elasticity equation. And I realized that I spelled that wrong, and I'm sorry. Elasticity. So once we have all our equations and our concepts down, we can just start solving problems. I think you're going to find that these problems are kind of fun. They're easy. They're not too hard mathematically. There's usually just 1 or 2 things that you figure out, and once you do it, you're done. So what I want to do is to give you a hint to help you get through those little issues that you might have in each problem. So let's start off with the first problem. Please remember, in the first problem, or in all these problems, there's numbers here. Your numbers are going to be different if you're doing this in Wiley Plus. So problem number 6 in chapter 12, this is a straight up equilibrium problem. We have a scaffold that's being held. A scaffold's just a thin bar. It's being held by a wire on each side. And then somewhere on here, there's a guy who's washing windows. So he's just standing there. We don't know the tensions in the wires, and we need to find them. So just remember that if I'm going to draw forces on here, there's always a force on the scaffold at the center of mass, at the center of the scaffold, which will be the mass of the scaffold times G. And wherever we put this guy, there's going to be a mass, I'm going to put W for window washer, times G. And then there's going to be a tension on the left for the wire, and there's going to be a tension on the right for the right wire. And those are our forces. So when we draw a free body diagram of the forces, we write one center of mass, we write tension left, tension right, weight of the window washer, and weight of the scaffold. Okay, we sum all these forces and we set them equal to 0. And that'll give us an equation. For our second equation, we choose a axis of rotation. So here, let's choose on the left. And so we have the scaffold, and we're going to look at how the torques may make this thing rotate either that way or that way, right? Since it's in equilibrium, they're not going to rotate. So what I do is I draw one torque vector, but let's draw all three. So this tension that's here, right? This tension on the left is acting at the axis of rotation, so we don't need to worry about it. Then we have the radius out to the guy and the mass of the guy times G. That is the torque due to the weight of the window washer. Remember that when we do these torques, we always put R and F tail to tail, and then we rotate R to F. So we see this is a negative torque, a negative alpha. And then the torque is simply RF with a negative sign here. This torque is negative RF. So this torque would be negative R to the guy times the mass of the guy times G. Then there's L to the half, which is the distance from here to the halfway point of the scaffold. That's where the weight of the scaffold is going to be. So mass of the scaffold times G. And then lastly, at that same axis, at a distance of L, we have tension to the right. And these two, obviously this is L to the half, mass of the scaffold times G. So this one's also a negative torque, and this one is L and tension to the right. So this one is a positive torque. And so all we have to do is sum the torques and set it equal to 0. And in this case, we would get L times tension to the right minus MWG times RW minus MSG times L to the half, or the distance. Now, RW here was given to me as 1.2 from the end. So he's 1.2 meters away. Once you solve this for T to the right, you know all this, you know the lengths, you know all these masses, you know all of these things. So you can solve this and get TR. You can use the sum of the forces, and we see from here that 0 is equal to TL plus TR minus MWG minus M scaffold G. From there, this problem is completely solved. The only issue that you may have doing this in Wiley Plus is that it wants it from the other side. So it wants to know how far away the guy is, I think, from the other side. Maybe I'm wrong on that, but if that's what it asked for, oh no, sorry. It wants the tension that's nearest to the person and tensions furthest away. I was thinking of a different problem. This problem's pretty easy. Sum up the torques, sum up the forces, set them equal to each other, or choose the right axis, and you'll eliminate either the left or the right tension. The only thing I would worry about here is make sure that You're always measuring your radial vectors from the axis of rotation. In this problem, I chose it from the left because I was given that he was 1.2 meters from the end. I knew all of my radial vectors here. I'll go over it more later, but for now, this is a pretty straightforward problem, pretty easy to do. Okay, problem 2, problem 10 actually, the second problem of the homework. This problem is one of those fun physics problems that once you figure it out, super easy. But you might stare at this for 10-15 minutes and not know what to do. You know this is equilibrium. You know that the sum of the forces in the x and the sum of the forces in the y have to be 0. And you think, well, also the torques have to be 0. Turns out we actually don't need the torques. But what is our system? And that's where things get a little iffy on here. Because if our system's everything, right, then we have a T1 here, and we have a T3 here, and we have an MAG here, and we have an MBG here, and inside here, we have a T2 and a T2. And I don't quite know what to do with these T2s, right? Well, that's the big giveaway here. If it's in equilibrium, then it's got to be in equilibrium about every point. And we can actually take it in equilibrium here and here. So let's put it around there and look at that. That one is going to have MHE and T2. And this one over here is actually going to have T2 as well. They're internal tensions, so they're going to disappear. But for now, write them. We need everything in X and Y, and we see that T1 is at this angle phi that they gave us. They gave us this angle phi. So we can break this up. Now remember, this is T1 and this is phi. Therefore, T1 in the Y direction is T1 cosine of phi. It's this vector along here if we look at this triangle, right? And T1 in X is actually negative. We don't need to worry about that, but negative T1 sine of phi. And now if I set the sum of the forces in X and Y to 0, I see that I get T1 cos phi minus MAG has to be 0. That's the sum of the torque, or the sum of the forces in Y. And I get T2 minus T1 sine phi is equal to 0. I was given this phi. And if I plug that stuff in, I can solve this for T1, plug that in here, and I can get T1 and T2. So far, so good. We're supposed to find T1 and T2. We can find the first two there. If we look over here at T3, we would have MBG, and then, as we did before, up would be T3 cos theta, and to the right would be T3 sine theta, because see, this section here is T3 cos theta, this vector, and this vector is T3 sine. But you don't really want to do that. It turns out that what you really want to do is you call this Tx, T3x, and call this T3y. And then you can solve that T3y minus MBG is 0, and T3x minus T2 is 0, and therefore you know that T3y is MBG and T3x is T2, and of course for any vector, T3x squared plus T3y squared, and the angle is the arctan of Ty over Tx, but in this case it's Tx over Ty because we're actually taking that angle there. So I think that's easy enough to do. It's a little bit of geometry and figuring out angles. The only real wrinkle here, and the point of this whole problem, is that if a system is in equilibrium, then the entire system is in equilibrium, which means at every point the forces should equal 0. And therefore we can break this into 2 equilibrium problems and get what we need from them. Fun little problem, pretty fast to do, not too bad. All right, so the third problem is problem 14. And here, this is a paint can problem, and I didn't show this, but this problem has a picture of a whole bunch of little paint cans, you know, everywhere on it. You can take the center of mass of the paint cans to be wherever their center of mass happens to be. And we're told that that's what we want to find. There's some distance from a horizontal cable. So we have a horizontal scaffold and it's suspended by 2 cables. And we're told in the picture that these 2 cables are at the ends. And we want to know how far from the cable on the right, okay? So how far should R to the paint cans be? Don't forget, at the center of the scaffold, we have the weight acting. So this problem is pretty easy. We can once again do what we did in the first problem and note that we have a tension on the left, we have a tension on the right, we have a mass of the scaffold times G, and we have a force that's the mass of the paint cans times G. But this time, we're told the tension on the right is 747 newtons. What we don't know is we don't know how far away from this. We don't know what R to the paint cans are, okay? We do know that the scaffold, at least in my problem, is 2.02 meters in length. So this is going to be 1.01. So let's redraw this over here as a torque diagram about the left. So I have a torque that's got to be R of the paint cans times the mass of the paint cans times G. I have another torque that is L to the half times the mass of the scaffold times G. And then I have a final that is L times the tension on the right. I don't need to worry about the tension on the left. Here, though, is what I was talking about in problem 1. Once you find R, it actually wants the full or the other distance. So you need to take what they're asking you for is R of P from the right. So R will be L minus R of P. It'll be the distance from here to here. So you just have to flip it. I mean, you could probably flip this problem and do it about, like do it from the other way and solve it, and it should be solvable. But either way, you're going to want to put the axis of rotation where the left tension is. You don't have that tension, and you don't need to solve for that tension. In this problem, you really just need to solve for the torque equation. The sum of the torques is equal to 0 will give you an equation that only has one unknown, the mass of the paint bucket, or the mass of the paint cans. Okay? And then you can figure out, the radius of the paint cans, and you can figure that out pretty fast and easy. The real Wiley plus problem is here. So again, this problem was meant to demonstrate that you can just use torques to solve for what you need, and to kind of hammer home that the center of mass of a bunch of masses is where all their mass acts like a point, as if it were all contained at that point, and we're trying to find that point for all the paint can masses. Okay? All right. This problem, problem 26, is essentially the ladder problem. And really, to tell you the truth, if you need a hint on this, This problem's all about finding angles. So if you go back to that ladder problem and you really know that ladder problem, you're fine here. But essentially, we need to know what the angle is before we do anything. And if we look, we can find the angle, right? Because we know that SOHCAHTOA, meaning cosine of an angle, is adjacent over hypotenuse. And in this case, I should write it big A. Our adjacent from the angle, our angle is here. Our adjacent is A, and our hypotenuse is L, okay? Yeah. It looks like the L's off, but remember that L's actually along his body. So the adjacent is little a, and this is L, and therefore our angle is our cosine of, for me, it would be the 0.985 over 1.90. But once I have the angle, everything else in this problem is super simple. If you need one other hint, let's draw the forces acting at each point. The wall is frictionless, the ground is not. So we have a normal force acting in the X direction. We have a normal force acting in the Y direction. We have his weight acting. We have his weight, which is mg, acting at a distance d. And then we have a force of friction acting in the negative X direction. And that's going to be mu n, okay? And so if I put my axis of rotation here, I don't have to worry about the friction or that. All I would have is his weight, mg, at a distance d, and at a distance L, I would have the normal in the X acting. Remember that those two torques, we need to take the perpendicular part of L and the perpendicular part of D. So really what we get is we get D, this part of D. So D cos theta times mg, and that is going to be a positive torque. It's trying to rotate it clockwise or counterclockwise. And then we have above here, so we need this distance up, and this distance up is L sine. So this distance is L sine of theta times the normal in the X direction. If you solve those two torques, you see that you get that the sum of the torques is 0 is d cos theta times mg minus L sine theta times nx. I can solve that. Let's look at that. D cos theta times mg is equal, move that to the other side, L sine theta and x, and therefore nx is equal to d over L times mg times cosine theta over sine theta, or cotangent, or 1 over tangent. Then, if we remember from our force diagrams, we know that nx has to be equal to mu n. The force this way has to equal the force that way, and ny has to be equal to nmg, but this is actually ny, okay? And so mu is nx over ny, and you've got something for nx, and right here, you know that ny is mg. So this ends up being d over L times 1 over tan theta. The only thing you had to solve for here was knowing how to get theta. So really, this is just a simplified ladder problem where they didn't give you the angle. It's not too hard. It's a really good practice problem, but it's super simple and you can do it in basically no time at all. I'm going to go back through it slower in a little bit, but hopefully that helps. So here, this problem, problem 49, is actually equilibrium plus elasticity. How you know that is in this problem, we immediately see that we're given Young's modulus. And if we're given Young's modulus, you can pretty much bet that you're going to use it for an elasticity. So recall that elasticity is F over A is Young's modulus, delta L over L. This F though, so we have the weight of this block times G, and we have a tension due to wire A, and we have a tension due to wire B. And it says that tension A got stretched, or that wire A got stretched. So the tension of A is our force. The tension acting on A was the force that caused this stretching. We're told that we know that these are circular wires, so they have a cross-sectional area of pi r squared, and we're given that pi, this is 1.2 times 10 to the minus 3 squared. So don't forget, when you square powers, they just add, so this would be 1.2 times 1.2 times 10 to the minus 6 times pi. We're told that the change in length was 1.85 millimeters, so 1.85 times 10 to the minus 3 meters. And we know that it was originally 2.60 meters long. Doing all this, solving this for F or TA, gives us TA. And once we have TA, the torques about the center are pretty easy because you have a dA and tension A, and you have a dB, tension B, and hopefully you can already see that this torque is trying to rotate it counterclockwise, this torque is trying to rotate it clockwise, and therefore the sum of our torques being equal gives us that dA TA has to equal dB TB. From our forces here, TA plus TB minus mg is equal to 0. We're told the mass of the log. We found TA, we can find TB. And then dA over dB is just TB over TA. That problem is just a pure computation problem and understanding the equilibrium of the torques and the forces. It's not too bad. It's another pretty fast problem. I don't think anyone really would have an issue doing this one. It was more of just a practice problem. So our final problem is purely an elasticity problem. And this problem has one of those really annoying physics wrinkles to it that I'm going to take you through. I don't expect anyone to get this right away without having some help. But we'll talk about it when we get there. So we know that there's Young's modulus, as mentioned. We have a machine that has a cylindrical aluminum rod with an initial length of blah and radius of blah. If it's cylindrical, that means that it's got a round cross-sectional area, right? It's a cylinder. It's being stretched by a machine pulling parallel to its length. And we notice that the radius decreases after it gets stretched. So it's thinner, right? The radius, the final radius and the initial radius are different. Initial radius was 893.5 times 10 to the minus 6 meters. The final is 893.2 times 10 to the minus 6 meters. Okay, so this thing, when it got stretched, we don't know what delta L is, but we got to figure out what delta L is. We're not given delta L though, we're just told that the radius changed. And that's where the problem comes in. So We're asked to find the magnitude of the force required to do this. And we know that F over A is Young's modulus times the change in length over the original length. So what we want is F is A times Young's modulus times delta L over L naught. And we're given Young's modulus as 70 times 10 to the 9 newtons per meter squared. We can easily figure out what the original cross-sectional, that would be the original cross-sectional area was. And we can multiply it by Young's modulus. What we don't know is what is delta L. So A initial here would be pi times 893.5 times 10 to the minus 6 squared meters. And length naught, as given above, would be the initial length was 0.6658 meters. And Young's modulus is 7 times 10 to the 10 newtons per meter squared. I guess I could write that better. Okay, but how do we find delta L? Well, we know that delta L is the final length minus the initial length. So we need to come up with some way to find the final length. Here it says that the rod's density, the mass per unit volume, does not change. The mass obviously can't change. Therefore, the volume cannot change. It's not realistic, but it's fine. So knowing that, the volume is pi r initial squared times length initial has to equal pi r final squared times length final. From this, you could find the final length as r initial squared over r final squared times the initial length, and then take LF minus L initial to get the change in length. That's the only wrinkle. That's the only issue you should have in this problem. Everything else is just plugging numbers in, to be honest. I suppose you could mess up and not realize that the cross-sectional area had to be the initial radius. But yeah, other than that, it's just a quick plug and chug where you had to find the length change. Not too hard. As I said, this is one that you could stare at for 15 minutes and have no idea how to do anything with it, which was why I gave it to you as a homework problem. All right, so for those of you who don't want any more help, this is the end of the video. Study hard. Our exam should be not too bad. Remember that mostly I want you to demonstrate how to set up the problems. That's what I care about the most. And I'm pretty sure I've covered all the problems that are on the exam. I think the exam's pretty easy with a couple little wrinkles. Anyway, let's get on to step by step. So let's go back to problem 6. As we did before, equilibrium problems, you have to start off by finding the sum of the masses and setting it, or the sum of the forces and setting it equal to 0, and the sum of the torques and setting that equal to 0. So we have a scaffold, and it has a wire, and it has a wire, and we have a guy standing here. Okay, for the force, free body diagram, we have the mass of the window washer times G, we have the mass of the scaffold times G, we have the tension in the wire to the left, and the tension in the wire to the right. So this is the left wire, this is the right wire. And one other thing we know, this whole distance is L. For me, that is a length of 5.4 meters. Okay, and we know that he is standing 1.2 meters away. Okay, So the sum of our forces is 0 is TL plus TR minus and window washer times G minus mass of scaffold times G, or that you have that TL plus TR is equal to these two masses times G. You don't know TL, you don't know TR. In fact, that's what you're looking for. But at least we have equation number 1. For the sum of the torques, we're going to choose the left side. And that means that we have R to the window washer, which was 1.2 meters. And the force acting on that is the mass of the window washer times G. Note that this is R and this is MWG, and this torque therefore is negative. Then we have at L to the half, always at the halfway point, you have the mass of the scaffold times G. So again, L to the half, mass of the scaffold times G. This torque is again negative. I'm putting them over here so you can see the tail to tail. And you always turn the radial to the force. It's R cross F, which means we cross R to F. And if we go in a clockwise direction, it's negative. If we go in a counterclockwise, it's positive. The final torque about that axis is actually at L, and it's the tension on the right. So here I have L and I have tension on the right, and that's positive. So the sum of my torques being equal to 0 is L times the tension on the right minus R to the window washer times G minus L to the half times mass of the scaffold times G. From this equation, which I'll write a little bit higher, I get that TR is equal to R of the windshield washer, mass of the windshield washer times G, plus L to the half times mass of the scaffold times G, all divided by the length. And once I find this, okay, I can then find TR or TL from this equation by substituting this in. I know the masses, I know G, 9.81. On an exam, you could use 10, but for Wiley Plus, please use 9.81 for G. Okay, so hopefully that's not too much trouble. Hopefully that's pretty self-explanatory. So again, for this one, the trick here was that we wanted, or we know that the system's in equilibrium. Therefore, we can take this as two equilibrium problems about these 2 points. And I'm going to call this point A and I'm going to call this point B. So I'm going to use the sum of the forces in X and the sum about A, the sum of the forces in Y about A, and the sum of the torques about A. These are all 0. I don't actually need to do torques in this problem. I could if I want to, but I'm not going to. So first step, draw a free body diagram. MA times G, and we know that this is tension 2. We need all our forces to be in either X or Y, okay? So T1, this vector right here, okay, this is T1, and it's at an angle phi to the positive, okay? They gave us phi as 39 degrees. So if I remember that for a vector that's just a right triangle, if this was T1, right, this would be T1 cos phi, and this would be T1 sine phi. So this is T1 cos phi, and this one here is T1 sine phi. All right, so let me draw those on my free body diagram. T1 cos phi, T1 sine v. The acceleration is 0. If you want to write it, I don't expect you to write it on equilibrium. You might want to choose an up positive or down positive, but it doesn't really matter. Since they're going to be equal to 0, and since the free body diagram tells you that, for example, in the x it's t2 minus t1 sine phi, I don't really ever write a on any equilibrium diagram. So from this, we know the sum in the x is 0, so for the x, and that is t2 minus t1 sine phi. In the y, which is also 0, we know we have t1 cos phi minus mag. Using this y equation, I get that t1 is mag times cos phi. So I've solved t1. This was the first thing that they wanted me to solve, part A. Once I have t1, I know that t2 is equal to t1 sine phi. And that gives me part B. And then we're going to do the second part. So the second part for B, we have mass of B down. We have mass of B times T down, the weight down. We have T2 again, but now this becomes T3 in the X, and this becomes T3 in the Y. So there's a, there's a T3 in the X, and there's a T3 in the Y. Resist putting this as T cos theta, T3 cos theta. Just leave it alone for a minute. So the sum of the forces in the X and the sum of the forces in the Y in this part of the problem, I get 0 is T3 of X minus T2. Remember, I already know T2. And I get T3 in the Y minus MBG, or obviously T2 is T3X and T3Y is MBG. Then I want to know the magnitude of T3 and I want to know the angle. And so the magnitude of anything is the X and Y components, which in this case, we said that T3Y is MBG and T3X is T2. I already have T2 from earlier, and I can get MBG because they gave me the mass. Then for the angle, I have to be a little bit careful because what they're actually asking me is for this angle. And so my Y here is my T3X and my X here is my T3Y, you know, my traditional I don't want to call that X and Y. Let's just put that way. So therefore, the arctan is normally Y over X, but our quote unquote Y here is T3X over T3Y, which is T2 over MBG. And so that'll give you the correct angle from the y-axis. Other than that, it's a lot of stuff we already knew. This problem's a bit of a headache because if you didn't realize every part of the system had to be in equilibrium, you might not have known to divide it up into two separate points. Other than that, I don't think this one's too hard. It's just a little bit of thinking that we love so much about physics. So okay, this one I more or less solved just like the first problem. It's the paint cans. But the difference here is that we have a scaffold. We have, again, a wire on the left, and we have a wire on the right. And we still have at the center the mass of the scaffold. And then somewhere here, we have this mass of the paint cans. It's at their center of mass, wherever the center of mass is. Remember back whatever it was, chapter 9 maybe, that we did center of mass briefly, maybe 8. It's at the center of mass of the cans. And then what they want to know is how far away it is. So they want to know the radius, and you know that for any radius you're going to have to use torque. But let's look at the forces. So we have the weight of the scaffold, the mass of the scaffold, times G, and we have the weight of the paint cans, and then we have tension on the left and a tension on the right. So the sum of the forces are only in Y, they're equal to 0. So 0 is T left plus T right minus M paint cans minus M scaffold. Okay. Then, knowing that you're going to be asked for the radius, you know that you're going to have to use torque. So we're told that T right is 747 newtons. Knowing that, it makes the most sense to just ignore tension 3. And to do that, we'll put our axis of rotation right, our tension on the left, right on the left. If there were a force acting here due to tension on the left, it is acting at the axis of rotation. Therefore, there can't be a torque because R is 0. Okay. So we only have 3 other torques. We have somewhere here, we have a radius to the center of mass of the paint cans times the weight of the paint cans. We have half the length. This whole thing, you're given the length of 2.02 meters here. So halfway is where the center mass of the scaffold itself will be located. So the weight there. And then finally, at the full length, the right-hand wire is creating a torque. These torques are equal to 0. So this tension is trying to rotate it. This one's trying to rotate it counterclockwise. Therefore, it is positive. These two are both trying to make it rotate clockwise. So they are both negative. RP, MPG minus L to the half M scaffold G. Solving this for T to the R, which I did do earlier, but I get RP, mass of the paint cans times G, plus L to the half, mass of the scaffold times G, all divided by the total length. Once I get TR, looking here, I know that TL is mass of the paint cans times G plus mass of the scaffold times G minus the tension on the right. So whatever this is, subtract the weight of the paint cans and the weight of the scaffold from it, and, well, subtract it from the weight of those two, and you'll get the tension on the left. Pretty easy to do. Oh, I'm sorry. I keep thinking this problem is asking me for something different. This problem only wants to know RP. So in this case, if I go back through and I solve it for RP, remember that I had the length times TR was equal to RPMG, MPG minus, plus L to the half, MSG, and I want to solve it for RP. So RP is equal to L to the half, M of scaffold G minus L times tension on the right, which I was given, divided by the mass of the paint cans times G. All I did was, minus and plus. All I did was I moved this over, and I then divided by that. So if you want to see this slower, MPG is equal to L T to the R minus L to the half M scaffold G, and then divide through by MPG. Okay, and this becomes 1. All right, that problem's pretty easy. Remember that it wants the distance from the right, and we measured the length from the left as 0 to L, and this will give us RP. But what it wants is it wants this distance R from the right. So R is going to be equal to L minus RP. It's going to be the distance from the left, or from the right, I mean, from the right wire. I hate when Wiley Plus does that. Unfortunately, it does that a lot. Okay, so this problem is the ladder problem. Essentially, we have friction on the bottom. We have no friction on the side. We have from here to here is L. We have some angle here. This distance from here to here is A, and there's a center of mass on the guy. So mass times G, where the weight is being applied. And that distance from here to here is D. Okay, so this whole length is L. This is D. This bottom length is A, just like it's shown. Second thing, forces. We're going to have a normal force off the wall that I'm going to call NX acting right here. There's no force up or down because there's friction on the wall, but there's still a normal force pushing him away. At the center of mass, of his mass, there's going to be a weight mg in the negative y direction. And at the floor, there's going to be a normal in the y and a force of friction, which is equal to mu times ny. That's going to stop him from sliding. He's right on the point of sliding. So we know this is static, but those are the four forces on his body. So for the first part, we sum the forces in the x and the y. So the sum of the forces in x and the sum of the forces in y are equal to 0. Some of the forces in x were nx minus the force of friction. I'm going to write this as nx is equal to the force of friction, which means nx is equal to mu ny, and we're trying to find mu, which it's easy to see, is nx over ny. So really what we're trying to find is this normal force at his feet and this normal force at his hands. Once we get those, we can solve for mu. In the y direction, we have normal y minus mg, and that just tells us that ny is mg. So we're halfway there. We have mg, and we don't know what nx is. So now, in order to find nx, the only thing we have left to do is use torque. So let's go down to the next page. And let's look at the torques acting. So you have a distance L. I'm going to choose the axis of rotation to be at his feet. Therefore, the force of friction and the normal force in the y direction, I don't care about those. But at a distance L, I have this normal force in the x acting. And at a distance D, I have this weight mg acting. Remembering that R cross F, which is the torque, is RF sine of the angle between R and F. But what this really means is it's R perpendicular times F. So for L and N, right, I need the perpendicular part of L. I need L perpendicular. L is my R vector here. If I call this angle some theta, then this L perpendicular is going to be L sine of theta. So therefore, this torque is going to be nx is equal, or sorry, nx, so the torque here is nx L sine of theta, or F and R, R and F. For the weight, I have D and I have mg, so I need D perpendicular. And D perpendicular, again, this is the same theta, is D cos theta. So this torque is going to be mg D cos theta, okay? And I don't know theta. But if I go back and I look here, I have L and I have A. And SOHCAHTOA means sine of the angle is opposite over adjacent. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So cosine, this is adjacent is little a. The A just means adjacent. Hypotenuse is L. So I have a triangle that looks like this. A and L, and I want to know what theta is. So if cos theta is little a over L, the adjacent over the hypotenuse, then theta is arc cosine of little a over L, okay? So I can find theta. I'm going to assume I know theta now. Now, my net torque is this torque positive or negative? Well, if I put L perpendicular and I put an X, I see that this is trying to rotate clockwise, so it's negative. It's a negative torque. L is trying to rotate. And then I have D perpendicular and I have mg. I really should have put these L and X so that you can see that we're turning clockwise. This one's turning counterclockwise, so it's positive. So this is 0 is D perpendicular, which is D cos theta mg minus nx L sine theta. Moving that over, I get that nx L sine theta is D mg cos theta. And finally, I get that nx is D over L times m times g times cos theta over sine theta. But this is simply 1 over tangent. So I have mu is nx over ny, and I know that this is mg, and I know that this is my dmg over L over 1. So this is dmg over L times tan theta. Which another way I could write this is, since tangent theta is opposite over adjacent, if I wanted to, I could write this as L sine theta, but I don't really want to do that. I'll just assume that you got that yourself. The masses cancel, so I get dl over tangent theta. And from there, we're good. From there, you know that this is, well, let's leave it at that. If you find that theta was arc cosine, theta is arc cosine of little a over L. Okay, and from there, we're all good. You solved this problem. All right. This problem. So we want to know the tension or the force on wire A, on wire B, and what the ratio between those distances are. And this problem, we start off using Young's modulus, noting that for Young's modulus, the force acting over the area is Young's modulus times the change in length over L. That this is in fact the tension on A over the cross-sectional area of A. is equal to Young's modulus times the change in length times L. We know delta L and L, we're given them. This is 0.00185 meters. And the original length was 2.60 meters. You might want to write length not. Doesn't really matter. Young's modulus is 2 times 10 to the 11th newtons per meter second. And the cross-sectional area for a circular wire, we're talking about these wires right here, is pi r squared, which is pi times 1.2 times 10 to the minus 3 squared. So remember that that's going to be 1.2 times 1.2 times 10 to the minus 6 meters squared. From all this, you can easily see that tension A is A cross-section, Young's modulus, change in length over length. Then let's look at the forces on this whole log. We have a tension A due to wire A and a tension B due to wire B, and a mass of the log times T. And therefore, TA plus TB minus mg is equal to 0. The sum of the forces in Y are equal to 0. So TA plus TB is equal to mg, and TB is equal to mg minus TA. So once I do that, I can get TA right here, I can get TB right here, and the only thing left is what is this ratio of dA to dB. So when I look, taking it through the center of mass, I could have this mg force, but that force is acting at the axis of rotation that I've chosen to go through the center of mass. So that force doesn't act. I have at dA, I have the tension due to A acting, and at dB, I have the tension due to B acting. If I sum these torques the way I normally have, so dA, TA, dA is rotating to TA, this is a negative torque. dB, TB, dB is rotating to TB, this is a positive torque. Sum of my torques is 0 is equal to dB, TB minus dA, TA. And obviously then, dA, TA is equal to dB, TB, or dA over dB is equal to TB over TA, and you've solved for those already here. So you have everything you need. Pretty simple stuff. Hopefully you understand that. It's a really simple equilibrium problem. Nothing majorly complicated at all to it, I don't think. Okay, and then our final was again this problem where you're stretching a aluminum cylinder, and that stretching is causing the radius to shrink. So you have to know that this is F over A is Young's modulus, delta L over L. But remember that this is the original area, this is the original length. What we want is the force here. We were given that the original length was 0.6658 for me. And we're given that the area, original area, we would know was pi times 893.5 times 10 to the minus 6 squared meters squared. We're given Young's modulus, 7 times 10 to the 10th newtons per meter squared. What we're not given, we're trying to find F, and we're not given our change in length. But we're told that the mass per unit volume does not change. We know that the mass cannot change. If the mass cannot change, if we're saying this is constant, and we're assuming the mass can't change, then the volume can't change either. And volume of a cylinder is L times pi r squared. So we say that the initial length, pi r squared, initial radius, is equal to the final length times the final radius squared. From this, the pi's cancel, and we get that the initial or the final length is the initial length times the initial radius squared over the final radius squared. And to get delta L, we need to subtract the final length from the initial length, or the initial length from the final length. Easy enough. Once we have that, this is just a plug and chug equation, you're done. Okay. Make sure that you understand how to do scientific notation. Remember that these R's are actually in millimeters. So this is 893.5 times 10 to the minus 6 squared will be 10 to the minus 12. So yeah, you're gonna have some weird big scientific numbers. But otherwise, I actually really like these 6 problems. They're pretty fast, pretty easy to do. I don't actually anticipate that you guys will need much help with any of these. I find this stuff pretty simple. The hard stuff is knowing what forces and knowing how to do torques. You have to know how to determine the torques. So hopefully these prepare you enough for the exam, and you'll have an understanding of equilibrium and elasticity. As always, stay healthy, stay safe, and I'll talk to you soon. Bye.